Jimmy Akin's Mysterious World is brought to you by the Star Quest Production Network and is made possible by our many generous patrons. If you'd like to support the podcast, please visit sqpn.com/give. You're listening to episode 348 of Jimmy Akin's Mysterious World, where we look at mysteries from the twin perspectives of faith and reason. In this episode, we're talking about the Kardashev scale. I'm Dom Bettinelli, and joining me today is Jimmy Akin. Hey, Jimmy.
Howdy, Dom.
Humanity has come a long way in the last few thousand years, but we may still have a long way to go. In science fiction, authors have dreamed up future civilizations with different levels of development. Some of them have colonized the solar system, like in the series The Expanse. Some stretch across multiple star systems, like the Federation in Star Trek. And some cover whole galaxies, like the Galactic Empire of Star Wars. All those are fiction, but is there any way of classifying such civilizations? Is there a way of making reasonable predictions about them? And could we use these predictions to find them? That's what we'll be talking about on this episode of Jimmy Akin's Mysterious World. Jimmy, where does our mystery start today?
It begins in Moscow in 1932 with a married couple, a man named Semyon and his wife Nina. They were patriotic Soviets. In fact, they were professional revolutionaries. Semyon was an important member of the Communist Party, and Nina had joined even before the October Revolution of 1917 that brought the communists to power in Russia. In 1932, Nina was pregnant with a son, and that son was born on April 25th, and they named him Nikolai. So, a happy event for Semyon and Nina. And Nikolai's boyhood name, by the way, was Kolya. Unfortunately, some not-so-happy events then proceeded to take place. Between 1936 and 1938, when Nikolai was between 4 and 6 years old, there was a series of events known as the Great Purge, or the Great Terror. This was an attempt by Soviet leader Joseph Stalin to consolidate his power over the Communist Party and to eliminate remaining influences of his former rival Leon Trotsky, who had gone into exile back in 1929. The Great Purge was a very bloody affair. It's estimated that it killed between 700,000 and 1.2 million people. Most of those were simply executed, but others died in the Gulag system of forced labor camps. During the Great Purge, both of Nikolai's parents became victims. His father, Semyon, was arrested and eventually shot, and his mother, Nina, was arrested and then sent to the Gulag forced labor camps. As a result, Nikolai was sent to an orphanage. Eventually, after a lot of effort, his aunt, his mother's sister, was eventually able to get him out of the orphanage. Meanwhile, Kolya's studies in school were progressing. As a fifth grader, he was very interested in astronomy, and he began attending the astronomy hobby group at the Moscow Planetarium. Unfortunately, another unhappy event then occurred, what is known in Russia as the Great Patriotic War, but which is better known here in the West as World War II. And Russia suffered particularly hard during the war, with intense fighting between the Soviets and the Nazis. Even more unfortunately, Nikolai's aunt died during the war. Nikolai then had to take care of himself and live on his own in a large communal apartment block. This was when he was 16 years old. In 1950, when he was 18, he entered Moscow State University, where he studied radio astronomy, which was a newly developing field that uses radio waves rather than visible light to study the universe. He received his degree in 1955 when he was 23, so another happy event for Nikolai. And then another happy event occurred. In 1956, his mother, Nina, after almost 20 years in the Gulag forced labor camps, and then more forced time in exile in the city of Murom, was finally allowed to return to Moscow. Yay! Nikolai then went on to have a distinguished career as an astrophysicist, and he survived into the 20th century. In fact, he didn't pass on to his reward until 2019 when he was 87.
So how is Nikolai Kardashev connected with our mystery today, and why is it named after him?
In 1964, when he was just turned 32, Nikolai published a paper called Transmission of Information by Extraterrestrial Civilizations, and in it he wrote this:
Calculations show that the total quantity of energy expended by all of mankind per second at the present time is about 4 times 10 to the 19th power erg. And the annual increase in this energy expenditure is placed at 3 to 4% over the next 60 years on the basis of statistical findings.
To understand this, you need to know that an erg is a unit of measurement for energy, and a single erg isn't much. It's a really teeny tiny amount of energy. But Kardashev is using an estimate that he says in 1963, mankind was using something like 4 times 10 to the power of 19 ergs every second. And 10 to the 19th means a 1 followed by 19 zeros, or 40 quintillion ergs per second. Put another way, that's 40 times a billion, or 40 billion billions of ergs per second, which is a lot. He also says that the amount of energy mankind is using is expected to grow by 3 or 4% every year over the next 60 years, which would bring us up to the year 2023, which we just had. However, he decides to be conservative and assume a growth rate of only 1% per year instead, and he makes this calculation.
Assuming x equals 1%, we find that the energy consumption per second will be equal to the output of the sun per second 3,200 years from now, i.e. 4 times 10 to the 33rd power erg per second, and that in 5,800 years the energy consumed will equal the output of 10 to the 11th power stars like the sun.
So Kardashev conservatively estimates that at a growth rate of just 1% annual energy output per year, we'll be using energy equivalent to that of our sun 3,200 years from now, which would be in the year 5,163, based on when he submitted the paper for publication. It didn't come out until 64. And he calculates that in 5,800 years, or the year 7763, we'll be consuming energy equivalent to 10 to the power of 11 suns. And there's a reason he picked that number, because 10 to the power of 11, or 100 billion, was an estimate for the number of stars in the Milky Way galaxy, although these days it's estimated that it may be 4 times as many as that. In any event, he calculates that by the 52nd century, we might be using as much energy as the sun puts out, and by the 78th century, we might be using as much energy as the galaxy puts out. He goes on to say,
in line with the estimates arrived at, it will prove convenient to classify technologically developed civilizations in 3 types. 1. Technological level close to the level presently attained on the Earth, with energy consumption at approximately 4 times 10 to the 19th power ergs per second. 2. A civilization capable of harnessing the energy radiated by its own star. For example, the stage of successful construction of a Dyson Sphere, energy consumption at approximately 4 times 10 to the 33rd power ergs per second. 3. A civilization in possession of energy on the scale of its own galaxy, with energy consumption at approximately 4 times 10 to the 44th power ergs per second.
So Kardashev proposed 3 basic types of civilizations: those with energy consumption equivalent to 1963 Earth, those with energy consumption equivalent to the output of our star, and those with energy consumption equivalent to the output of the stars in our galaxy.
One of the things he mentioned is a Dyson Sphere. Not everyone may be familiar with that, so what are Dyson Spheres?
They're a concept that was popularized by the physicist and mathematician Freeman Dyson, though they were actually thought up earlier, apparently by the science fiction writer Olaf Stapledon in his 1937 novel The Star Maker. But Dyson put them on a firmer theoretical foundation in a 1960 paper he published, and his name became attached to them. In simplified form, the idea of a Dyson sphere is that you build a big shell around a star, and then you use the inner surface of that shell to harvest all the solar energy that the star is putting out. So if you could build a Dyson sphere around our sun, you could harvest the approximately 4 times 10 to the 33 ergs that it puts out every second, if you had the entire inner surface of the shell covered with solar collectors.
Is that a practical idea?
Well, certainly not for a civilization at our level, and I should note that Dyson said this wasn't exactly what he had in mind. He later pointed out that there's no way to build a full sphere around a star for mechanical reasons. The materials just wouldn't take the strain. Though that didn't stop the USS Enterprise D from finding Captain Montgomery Scott crashed on the surface of a Dyson Sphere in the Next Generation episode Relics. And strangely, the captain didn't explain that the materials that the sphere was made out of cannot take the strain. In any event, even though Dyson referred to it as a shell in his 1960 paper, he said that what he actually had in mind was a loose collection or swarm of independent objects moving around the star in their own orbits. As a result, people now often refer to Dyson swarms instead of Dyson spheres. These would be just one kind of megastructure that you could build around a star to collect energy, though. And there's nothing in principle impossible about them. They don't violate the laws of physics. Just don't expect mankind to build one anytime soon. Though that would be one way that humanity could jack itself up into being a Type 2 civilization on the Kardashev scale.
Okay, we've now explained the basics of the Kardashev scale, but why is this a mystery?
It's not the Kardashev scale itself that is mysterious. It's the subjects that the Kardashev scale is connected to that are, and how the scale might help us figure them out. So we'll introduce the mysteries as we go.
Kardashev suggested his scale over 60 years ago now. What's happened with the idea since he proposed it?
Well, it took off, and it made Kardashev famous. It's the thing he's most known for today, and a bunch of authors have begun using the concept, included in popular-level works. For example, in his book, The Physics of the Impossible, American physicist Michio Kaku describes the scale this way.
Type 1 civilizations, those that harvest planetary power, utilizing all the sunlight that strikes their planet. They can, perhaps, harness the power of volcanoes, manipulate the weather, control earthquakes, and build cities on the ocean. All planetary power is within their control. Type 2 civilizations, those that can utilize the entire power of their sun, making them 10 billion times more powerful than a Type 1 civilization. The Federation of Planets in Star Trek is a Type 2 civilization. A Type 2 civilization, in a sense, is immortal. Nothing known to science, such as ice ages, meteor impacts, or even supernova, can destroy it. In case their mother star is about to explode, these beings can move to another star system, or perhaps even move their home planet. Type 3 civilizations, those that can utilize the power of an entire galaxy. They are 10 billion times more powerful than a Type 2 civilization. The Borg in Star Trek, the Empire in Star Wars, and the galactic civilization in Asimov's Foundation series correspond to a Type 3 civilization. They have colonized billions of star systems and can exploit the power of the black hole at the center of their galaxy. They freely roam the space lanes of the galaxy. Kardashev estimated that any civilization growing at a modest rate of a few % per year in energy consumption will progress rapidly from one type to the next within a matter of a few thousand years to tens of thousands of years.
So that's Kaku's basic explanation for the scale, but I'd note a few things. First, the Borg may not be as Type 3 as he supposes. In fact, far from being immortal, the Borg apparently are destroyed in Picard Season 3. Also, neither the Star Wars Galactic Empire nor the one in Asimov's Foundation series are using the starlight of every sun in their galaxies. They may span across their galaxies, but they haven't wrapped all the stars in Dyson spheres and created dark galaxies. This brings us to an imprecision in Kaku's explanation. He says that Type 1 civilizations use all the sunlight that strikes their planet. He says that Type 2 civilizations can utilize the entire power of their sun, and he says that Type 3 civilizations can utilize the power of an entire galaxy. But none of those are exactly what Kardashev said. All Kardashev did was define civilizations in terms of how many ergs of power they used per second. He didn't address where the power came from. He suggested a Dyson sphere as a way a Type 2 civilization could power itself, but properly speaking, there's nothing in his definition telling us where the power comes from. It could come from anywhere. So instead of being powered by a Dyson Sphere, a Type 2 civilization might be using antimatter, for example, or it might have massive solar collectors around several stars, even though none of them is a Dyson Sphere or swarm. The important thing to understand is that it's not where the energy comes from that's important. It's what the energy is equivalent to, whether that's the whole galaxy of suns or an individual sun or the sunlight falling on an individual planet. And that brings us to another issue with Kaku's explanation. He's defined Type 1 as a civilization using all the sunlight falling on a planet. But that's going to vary widely by what planet you're talking about, what star you're talking about, and what the distance is between the planet and the star. For example, Mercury is much smaller than Earth, so if it were at the same distance from the sun as Earth is, it would get much less power from the sun than Earth does. While Jupiter is much larger than Earth, so if it were at the same distance from the sun that Earth is, it would get much more power from the sun than Earth does. I thus have to conclude that what Kaku is imagining is an Earth-sized planet at an Earth-sized distance from a sun-like star, and he's simply speaking in a non-technical way for the sake of his audience's comprehension.
But even then, there's a shift in how he's defining Type 1. In his original paper, Kardashev defined Earth in 1963 as Type 1, but Earth wasn't close to using all the sunlight that falls on the planet in 1963. We aren't even there in 2024.
Yeah, that's correct. There has been a shift in how people are defining Type 1, and I'm not sure who introduced the change. But even though Kardashev defined us as Type 1 in the original paper, a lot of people aren't doing that now. For example, Michio Kaku writes,
As I discussed in my previous books, our own civilization qualifies as a Type 0 civilization, i.e. we use dead plants, oil, and coal to fuel our machines. We utilize only a tiny fraction of the sun's energy that falls on our planet. But already we can see the beginnings of a Type 1 civilization emerging on the Earth. The internet is the beginning of a Type 1 telephone system connecting the entire planet. The beginning of a Type 1 economy can be seen in the rise of the European Union, which in turn was created to compete with NAFTA. English is already the #1 second language on Earth and the language of science, finance, and business. I imagine it may become the Type 1 language spoken by virtually everyone. Local cultures and customs will continue to thrive in thousands of varieties on the Earth. But superimposed on the mosaic of peoples will be a planetary culture, perhaps dominated by youth culture and commercialism.
I agree with Kaku that all the signs he mentions of an emerging global civilization are real, but I don't like the fact that the Kardashev scale has been redefined so that we're now a Type 0 civilization. People who do that are just being party poopers. It only makes sense that we get to be at the beginning, or Type 1, of a civilization scale at the time it's defined.
And Type 0 is a little blunt and unsophisticated. That makes it sound like we're back in the Stone Age or something. And we've come way beyond that in terms of technological progress.
And this points out one of the problems with the Kardashev scale. It isn't fine-tuned enough. There are a wide range of different levels of power consumption that a civilization may have, and putting them into just 3 buckets, or 4 if you count Type 0, isn't enough. I have my own way of solving this, which we'll talk about in the reason perspective, but others have noted the same problem, and one of them was Carl Sagan. In the 1970s, he reverse engineered a logarithmic formula for the Kardashev scale based on power usage. This would let you calculate incremental steps between the major levels. Kind of like on Star Trek, you don't have to go warp 6 and then leap immediately to warp 7. You could go warp 6.1 or warp 6.2 or whatever. In the same way, using Sagan's formula, you don't have to be Type 1, Type 2, or Type 3. You have intermediate stages like Type 1.1 or Type 1.9 or Type 2.5, or even more finely grained ones like Type 1.15 or Type 1.16 or whatever.
In that case, you could have intermediate stages between Type 0 and Type 1. So where would Earth's present state of development fall?
In his 1973 book, The Cosmic Connection, Sagan calculated that in the 1970s, Earth was using between 10 to the 15th and 10 to the 16th watts. a watt being 10 million ergs per second. So it's easy to convert ergs per second into watts. You just divide by 10 million. And the amount of power we were using in the 1970s would give us a Kardashev type Rankine of 0.7. So close to a type 1, but not there yet.
Of course, we've made progress in the more than 50 years since 1973.
Yeah, our power consumption has grown, so now we're even closer to type 1, but not by that much since the scale is logarithmic. In 2021, human power usage was estimated at 18.87 terawatts, so almost 10 to the power of 19 watts. And that would work out to a type 0.73 civilization.
So when can we expect to hit type 1?
Well, this gets us into one of the mysteries connected with the Kardashev scale. To estimate how soon we'll reach type 1, we have to assume two things. First, that there will be no major disasters that set civilization back or even end it entirely. And second, that recent trends in power consumption growth will continue at the same rate. And neither of those assumptions is a sure thing. First, we're currently at a uniquely vulnerable stage. In The Physics of the Impossible, Kaku writes,
"The transition between one civilization and the next is far from guaranteed. The most dangerous transition, for example, may be between a Type 0 and a Type 1 civilization. A Type 0 civilization is still racked with the sectarianism, fundamentalism, and racism that typified its rise. And it is not clear whether or not these tribal and religious passions will overwhelm the transition. Perhaps one reason that we don't see Type 1 civilizations in the galaxy is because they never made the transition, i.e. they self-destructed. One day, as we visit other star systems, we may find the remains of civilizations that killed themselves in one way or another. For example, their atmosphere has become radioactive or too hot to sustain life."
So here, Kaku envisions Type 0 civilizations destroying themselves as they approach Type 1 by nuclear wars or global warming, both of which are things we'll discuss in future episodes. And artificially caused disasters like this are one of the solutions to the so-called Fermi paradox, which we discussed way back in episode 10. Basically, the Fermi paradox is why we don't see evidence for other intelligent life in the universe if it can commonly arise. It should have reached us by now, or at least be detectable. But there are a bunch of solutions to the Fermi paradox, and one class of them relies on what's known as the Great Filter hypothesis. It holds that there are one or more great filters that tend to eliminate intelligent life before it becomes detectable to us. That filter could lie in our past, like maybe life is really hard to get started in the first place, and we just got lucky to get past that filter or those filters. Or such a filter could lie in our future, like nuclear war or artificial intelligence or some other byproduct of technology that causes intelligent races to rapidly go extinct. You could even propose a religious great filter explanation, like maybe God comes back to a world where he created intelligent life before it can become a Type 2 civilization and start spreading out to interfere with other civilizations in other star systems. And when God comes back, he performs the resurrection of the dead and advances the world to the eternal order, or moves its inhabitants to a new universe, or does whatever is represented by the Bible's statement that one day God will create a new heaven and a new earth, whether that's in terms of renovating the existing world or building a new one. But more common proposals are things like nuclear war and major environmental shifts. But neither nuclear war nor global warming has to end all life on a planet, or even all intelligent life. But as they say, one nuclear bomb can ruin your whole day. And so even if a nuclear exchange doesn't kill all intelligent life, it can knock a civilization back on the technological development scale, either all the way back to the Stone Age or somewhere in between. The same would be true of intelligently caused environmental disasters. They thus might slow progression to a Type 1 civilization, but not stop it entirely. Elsewhere, in an article on his website that we'll have a link to, Kaku considers other possibilities. He writes,
By definition, an advanced civilization must grow faster than the frequency of life-threatening catastrophes. Since large meteor and comet impacts take place one every few thousand years, a Type 1 civilization must master space travel to deflect space debris within that time frame, which should not be much of a problem. Ice ages may take place on a timescale of tens of thousands of years, so a Type 1 civilization must learn to modify the weather within that time frame.
What Kaku says here of Type 1 civilizations also applies to those that have not yet reached that status. They're also vulnerable to natural disasters like asteroids and comet impacts, and extreme but natural changes like in climate like ice ages. There also are things like massive volcanic eruptions. We've already had each of those in Earth's history, the most famous impact being the one that killed the dinosaurs 65 million years ago and that ended any intelligent civilization they might have had, something that's known as the Silurian hypothesis, based on the Silurians from Doctor Who. We'll also talk about the Silurian hypothesis in a future episode. And we've had major volcanic eruptions. It's speculated that these may have contributed to the extinctions of the dinosaurs, a theory we'll also discuss in the future. And even in human history, we've had massive volcanic super eruptions, like the youngest Toba eruption, which occurred about 74,000 years ago on the island of Sumatra. This was a level 8 eruption on the Volcanic Explosivity Index, and it's referred to, therefore, as a megacolossal explosion. It ejected between 2,000 and 3,000 square kilometers of dense rock, and there have been pre-human explosions several times larger than that. But some have proposed that the Toba eruption caused an ice age, which then caused a human population bottleneck that reduced the human population to between just 1,000 and 10,000 people. That leads us to the topic of ice ages. And of course, despite all the global warming warnings that you hear in the media, we're actually still living in an ice age. It's known as the Quaternary glaciation or the Pleistocene glaciation. We've been fortunate to be living in a somewhat warmer period of it, so the level of glaciation is not as high as it has been, but we still have regular ice coverage at both the North and the South Poles, which is what defines when the Earth is in an ice age and when it isn't. We don't always have ice up there, but we do now, so we're still in an ice age. And it's notable that we've only begun to make technological progress since the last major glaciation began to recede between about 11 and 12,000 years ago. So you could easily argue that we'd already be a Type 1 or even a Type 2 or 3 civilization, except for the fact that we've been dealing with an ice age and a recent period of high glaciation here on Earth. In any event, all the major climatic shifts can also delay technological progress. So there are a number of factors that could slow our progression to Type 1 status, like a nuclear war, or an asteroid or comet impact, or another period of high glaciation like they were speculated about in the 1970s. Ironically, if man-made global warming is a thing, it might help us get to Type 1 faster. But if any of those other things happens, it could slow us down in achieving Type 1 under the newer conception of what Type 1 means.
You mentioned that it's also not guaranteed that recent trends in power consumption growth will continue at the same rate they've been. What were you thinking of here?
Well, it's been noted that we haven't made a lot of new fundamental discoveries in science in the last 50 years. We've made lots of small incremental discoveries, but no big new fundamental ones. For example, the standard model of particle physics was developed by the mid-1970s, and everything we found out about particle physics since then has just been minor fiddling with the parameters. The same thing is true in other areas of science, and no one is sure why. One theory is that something has gone wrong with the way we're doing science. In other words, that we've created a set of incentives for scientists, and that set of incentives has resulted in a lot of low-level stuff being done when there are really big discoveries waiting to be found, but scientists just aren't properly incentivized to find them. In other words, we don't currently know how to organize scientific research properly to get at the big solutions that are out there. Another theory is that we've already found all of the low-hanging fruit in science, and so there are no new big discoveries waiting to be found in the foreseeable future. In other words, we've hit something of a wall when it comes to what our current technology can discover, and we can expect diminishing returns for an indefinite future. This is argued, for example, in John Horgan's book, The End of Science, Facing the Limits of Knowledge in the Twilight of the Scientific Age. Although, towards the end of his life, Horgan began to have doubts about his own proposal. I track the discussion of these matters, and I don't claim to know who's right. I suspect that the correct answer may involve a bit of both approaches. In other words, we may have picked a lot of the low-hanging fruit, but we've also disincentivized scientists from finding what remains. For example, the taboo on doing parapsychological research can easily be argued as keeping our knowledge of that science low. However, since technological development is dependent on scientific advancement, the slowing of scientific discovery for whatever reason implies an eventual slowdown of technological development. And so, if things don't change, we may see slowdowns of technology, including those that involve power generation, in which case our progress towards type 1 could also slow.
Okay, so assuming that we don't face a man-made or natural disaster and that the rate of power consumption continues to increase at current rates, when can we expect to achieve type 1 status?
Well, estimates vary, of course. In fact, under Kardashev's definition, we're already type 1, but authors have made different estimates under the alternative conceptualization. On the short scale, planetary physicist Philip Metzger estimates that we're already approximately there. It's not clear to me that he's using the same definition as Sagan and others, but in 2011 he wrote,
"Building a starship within the next 100 years is an audacious goal. To be successful, we need sustained funding that may be difficult to maintain in the face of economic challenges that are poised to arise during the next 100 years. Our species' civilization has only recently reached the classification as approximately type 1 on the Kardashev scale. That is, we have spread out from one small locality to become a global species, mastering the energy and resources of an entire planet. In the process, we discovered the profound truth that the two-dimensional surface of our world is not flat, but has positive curvature and is closed so that its area and resources are finite. It should come as no surprise to a Type 1 civilization when its planet's resources dwindle. How could they not? Yet we have gone year by year, government by government, making little investment for the time when civilization becomes violent in the unwelcome contractions that must follow. When we are forced too late into the inevitable choice to remain and diminish on an unhappy world, or to expand into an only dimension remaining perpendicularly outward from the surface into space, then someday we may become a Type 2 civilization, mastering the resources of an entire solar system. Our species cannot continue as we have on this planet for another 100 years. Doubtless it falls on us today, the very time we intended to start building a starship, to make the late choice. We wish this century to be filled with enlightenment and adventure. It could be an age of desperation and war. What a time to begin an audacious project in space. How will we maintain consistent funding for the next 100 years? Fortunately, saving a civilization, mastering a solar system, and doing other great things like building starships amount to mostly the same set of tasks. Recognizing what we must be about during the next 100 years will make it possible to do them all.
So Metzger estimates that we're already approximately at Type 1, but he thinks that we face a bunch of resource problems in the coming century. And things are likely to get bad if we don't undertake the project of building a starship. Not just a spaceship, but a starship that could take us to another star. If we don't do that in the next 100 years, he thinks things could get bad. But undertaking that project will enable us to tap the resources of our solar system and, in his view, help us make the leap to Type 2.
What do you make of this view?
Well, I don't dismiss it out of hand, but I also don't accept it uncritically. His paper came out in 2011, and that was the same year that gas in the United States hit basically $4 a gallon, or $5.50 per gallon after the inflation the government has caused since then. And at that time, President Obama said things like, we can't just drill our way out of the problem. But President Obama was wrong. We did drill our way out of the problem due to both new technologies and less government regulation. Today, the price of a gallon of gas has fallen by 43% from its peak in 2011, and the United States has become the largest exporter of crude oil in the world, outranking both Saudi Arabia and Russia. And there doesn't seem to be a sign that that's going to change anytime soon. Now, obviously, Earth's resources are finite and they will run out at some point. And things may have looked bleak back in 2011 when Metzger wrote his paper, but they weren't as bad as he thought. And we may not be near as close to the point of running out of resources as he thought we were.
What have others said about when we'll hit Type 1?
Carl Sagan estimated that we'd reach it around the year 2100, so that's just 75 years from now. Michio Kaku similarly estimated it'll be in 100 to 200 years from now, so between 2125 and 2225. And Freeman Dyson agreed with the 200-year estimate, so 2225. On the other hand, physicist Richard Wilson estimated that if it arrives soon, it would be around the year 3000. So there's a considerable range of estimates, but the majority of the ones that I've come across seem to think between 75 and 200 years.
Any idea when we might reach Type 2 or Type 3?
Well, the further you go into the future, the less accurate predictions become. So it's even harder to predict that than it is the transition to Type 1. And it's really not possible to make anything other than educated guesses that assume current trends continue, in which they are very likely not to continue, especially given the religious constrictions suggested by the apparent New Testament vision of human eschatology, which we'll talk more about in the faith perspective. However, assuming a 1% growth in energy consumption per year, Nikolai Kardashev estimated that we would reach Type 2 in the 52nd century, about the year 5163, and he estimated that we'd reach Type 3 in the 78th century, or about the year 7763. So both of those estimates were within the next 6,000 years. Michio Kaku, the only other author I found who's willing to venture such estimates, is less optimistic. In a piece called The Physics of Interstellar Travel, he writes,
growing at the average rate of about 3% per year, one may calculate that our own civilization may attain Type 1 status in about the next 100 to 200 years, Type 2 status in a few thousand years, and Type 3 status in about 100,000 to 1,000,000 years. These timescales are insignificant when compared with the universe itself.
So that's the origin of his estimate of 100 to 200 years to Type 1. And his estimate of a few thousand years to Type 2 agrees with Kardashev, who estimated it would be about 3,000 years before we get there. But Kaku is much more pessimistic in terms of reaching Type 3. Kardashev thought it would be within 6,000 years, but Kaku estimates it would be 100,000 to 1,000,000 years.
What do you think?
Well, I don't have any special insight into the growth curve of human power consumption, so I largely have to defer to experts on that matter. But to anticipate the faith perspective when it comes to theological reasons, I'm more pessimistic than either Kardashev or Kaku. I think God may well allow us to reach Type 1 status in the next 100 to 200 years, and I think it's at least hypothetically possible he might allow us to reach a little beyond that into Type 2 territory, but I think it is quite unlikely that he would allow us to have a robust interstellar civilization before Jesus comes back, and I think it's very unlikely that he would let us have a galactic civilization before that occurs. So I think it's sharply and progressively less likely that we will get too much further down the scale than we are now. We may still have hundreds or even thousands of years to go, especially considering setbacks that civilizations can face, but I think we're unlikely to get to the higher Kardashev levels. Still, that doesn't stop us from imagining them in science fiction or considering them in principle, meaning considering them if God doesn't do something to alter our progression.
Then, instead of talking about when we may reach these levels, let's talk about what civilizations that could achieve them might do. What could a Type 1 civilization do that we could not?
Well, for a start, we'd have more control over what happens here on Earth. In his article on the physics of extraterrestrial civilizations, which I will henceforward refer to as his civilizations paper, Michio Kaku writes,
"A Type 1 civilization is a truly planetary one which has mastered most of its forms of planetary energy. Their energy output may be on the order of thousands to millions of times our current planetary output. Mark Twain once said, 'Everyone complains about the weather, but no one does anything about it.' This may change with a Type 1 civilization, which has enough energy to modify the weather. They also have enough energy to alter the course of earthquakes, volcanoes, and build cities on their oceans. Artificial and internal catastrophes must also be negotiated. But the problem of global pollution is only a mortal threat for a Type 0 civilization. A Type 1 civilization has lived for several millennia as a planetary civilization, necessarily achieving ecological planetary balance. Internal problems like wars do pose a serious recurring threat, but they have thousands of years in which to solve racial, national, and sectarian conflicts."
And in addition to things we could do here on Earth as a Type 1 civilization, we'd also be able to explore our own solar system thoroughly and set up stations and colonies elsewhere in the solar system and even begin exploring other nearby star systems. In his Physics of Interstellar Travel paper, which I will henceforward refer to as his travel paper, Kaku writes,
"Propulsion systems may be ranked by two quantities, their specific impulse and final velocity of travel. Specific impulse equals thrust multiplied by the time over which the thrust acts. At present, almost all our rockets are based on chemical reactions. We see that chemical rockets have the smallest specific impulse since they only operate for a few minutes. Their thrust may be measured in millions of pounds, but they operate for such a small duration that their specific impulse is quite small. NASA is experimenting today with ion engines, which have a much larger specific impulse, since they can operate for months, but have an extremely low thrust. For example, an ion engine which ejects cesium ions may have the thrust of a few ounces, but in deep space they may reach great velocities over a period of time since they can operate continuously. They make up in time what they lose in thrust. Eventually, long-haul missions between planets may be conducted by ion engines. For a Type 1 civilization, one can envision newer types of technologies emerging. Ramjet fusion engines have an even larger specific impulse, operating for years by consuming the free hydrogen found in deep space. However, it may take decades before fusion power is harnessed commercially on Earth, and the proton-proton fusion process of a ramjet fusion engine may take even more time to develop, perhaps a century or more. Laser or photonic engines, because they might be propelled by laser beams inflating a gigantic sail, may have even larger specific impulses. One can envision huge laser batteries placed on the moon, which generate large laser beams, which then push a laser sail in outer space. This technology, which depends on operating large bases on the moon, is probably many centuries away.
So here Kaku mentions several ways of getting from place to place in space. There are chemical rockets, which we have now, but they're really slow. We're also near to getting ion drives that expel ions out the backs of ships instead of dependent on chemical reactions. He says that at Type 1, we might have ramjet fusion engines. In airplanes, a ramjet is an engine that takes in air as it moves forward and then compresses that air to turn it into thrust, which comes out the back of the engine. The idea here is for a starship engine that takes in hydrogen from the interstellar medium between stars and then compresses the hydrogen to the point that nuclear fusion happens, creating thrust. Finally, Kaku mentions light sails, which you can make more dependable and faster if you shine big lasers on the sails to generate more thrust. And the logical way to do that is to use big laser cannons mounted on a planetary surface, like that of our sister planet, the Moon, because that way you don't have to burden the ship with all the weight of the cannons and the power generating equipment and the fuel that you need to run them. And I found it interesting that Kaku doesn't mention a couple of other types of transport that have been proposed. One is the Orion class or style of drive, which basically uses nuclear bombs for thrust. You build a ship that carries a bunch of nuclear bombs, and you drop them behind the ship one at a time and blow them up to push the ship forward. This is, incidentally, one of several possible moral uses for nuclear weapons. Then there's the Daedalus class or Daedalus style of drive, which uses an onboard fuel system to drive a nuclear fusion motor to generate thrust. We currently have uncontrolled nuclear fusion, which is what a hydrogen bomb is. But if we can figure out how to bring it under control, then we could build Daedalus-style drives. And any of these methods, except the chemical and maybe ion rockets, would let us not only colonize our own solar system, but also explore nearby ones, at least using robotic probes. In fact, robotics would allow us to explore a lot of solar systems while we're at a Type 1 civilization stage. In this connection, Kaku mentions what are known as von Neumann probes, and he says,
"The most mathematically efficient method to explore space is to send fleets of von Neumann probes throughout the galaxy, named after John von Neumann, who established the mathematical laws of self-replicating systems. A von Neumann probe is a robot designed to reach distant star systems and create factories which will produce copies of themselves by the thousands. A dead moon rather than a planet makes the ideal destination for von Neumann probes, since they can easily land and take off from these moons, and also because these moons have no erosion. These probes would live off the land, using naturally occurring deposits of iron, nickel, etc. to create the raw ingredients to build a robot factory. They would create thousands of copies of themselves, which would then scatter and search for other star systems. Similar to a virus colonizing a body many times its size, eventually there would be a sphere of trillions of von Neumann probes expanding in all directions, increasing at a fraction of the speed of light. In this fashion, even a galaxy 100,000 light-years across may be completely analyzed within, say, 500,000 years."
Of course, we wouldn't still be a Type 1 civilization after 500,000 years. We'd be Type 2 or Type 3 if we're still around. But we could get a start on this type of galactic exploration while we're at Type 1. This is one of the reasons why the Fermi paradox is a paradox, because any advanced civilization out there should have found us by now using von Neumann probes, at least if they're interested in building von Neumann probes. But there may be an explanation for why we haven't noticed any.
If a von Neumann probe only finds evidence of primitive life, such as an unstable savage Type 0 civilization, they might simply lie dormant on the moon, silently waiting for the Type 0 civilization to evolve into a stable Type 1 civilization. After waiting quietly for several millennia, they may be activated when the emerging Type 1 civilization is advanced enough to set up a lunar colony. Physicist Paul Davies of the University of Adelaide has even raised the possibility of a von Neumann probe resting on our own moon, left over from a previous visitation in our system eons ago. If this sounds a bit familiar, that's because it was the basis of the film 2001. Originally, Stanley Kubrick began the film with a series of scientists explaining how probes like these would be the most efficient method of exploring outer space. Unfortunately, at the last minute, Kubrick cut the opening segment from his film, and these monoliths became almost mythical entities.
So it could be that there is a von Neumann probe right now on our moon at the moment. We just haven't found it yet. It's also possible that we're even surrounded by such probes, but haven't noticed them.
Nanotechnology may facilitate the development of von Neumann probes. As physicist Richard Feynman observed in his seminal essay, "There's plenty of room at the bottom," there is nothing in the laws of physics which prevents building armies of molecular-sized machines. At present, scientists have already built atomic-sized curiosities, such as an atomic abacus with buckyballs and an atomic guitar with strings about 100 atoms across. Paul Davies speculates that a spacefaring civilization could use nanotechnology to build miniature probes to explore the galaxy, perhaps no bigger than your palm. Davies says, "The tiny probes I'm talking about will be so inconspicuous that it's no surprise that we haven't come across one. It's not the sort of thing that you're going to trip over in your backyard. So if that is the way technology develops, namely smaller, faster, cheaper, and if other civilizations have gone this route, then we could be surrounded by surveillance devices."
And since we're already learning to do nanotechnology, we could build nanotech-based von Neumann probes while we're at the Type 1 stage, which would allow us to get them to other stars more easily because of their small size and thus their low weight.
If those are some of the things we could achieve as a Type 1 civilization, what might we do as a Type 2?
Well, for one thing, we'd be a lot harder to kill. Currently, a major asteroid strike could take us out, like what happened to the dinosaurs, or so it seems. But if we can get all of our eggs out of the same basket, which is to say, if we can get off Earth, then no planetary disaster could kill us. And by the time we'd reach Type 2, we'd already be in other solar systems, so even the death of our own sun wouldn't do us in. The only thing that would be likely to wipe out all humans at that point would be a nearby supernova that would irradiate all of the nearby star systems with a kill and blast of X-rays, and even that might not do it. Also, by this point, we'd have really remarkable power over our own solar system, and so many of the principal things we might do would involve space. For example, if a Type 2 civilization needed to modify the way that its star burns or to extend its star's life, it might do what's known as stellar seeding, which is where you add new matter to the star to change the way it burns, like giving it extra nuclear fuel so that it doesn't run out and go through the normal end stages of the star's life, or stabilizing the way it burns in case it's developed irregularities. Type 2s also could have new ways to get across space. One way to do that might be a little surprising to people, but it's to move your star. For example, if you were too close to a neighboring star that might go supernova and kill you, or if you were entering a hazardous region of the galaxy, you could use a Dyson swarm around your star as a kind of stellar engine to slowly push it in the direction you wanted to go. It'd take a long time, but it would be quite possible by reflecting and redirecting sunlight on the same principles that are used with solar sails, which are another form of light propulsion. And there would also be additional means of transportation opening up. In his travel article, Kaku writes,
For a Type 2 civilization, a new form of propulsion is possible: antimatter drive. Matter-antimatter collisions provide a 100% efficient way in which to extract energy from matter. However, antimatter is an exotic form of matter which is extremely expensive to produce. The atom smasher at CERN outside Geneva is barely able to make tiny samples of anti-hydrogen gas, anti-electrons circling around antiprotons. It may take many centuries to millennia to bring down the cost so that it can be used for spaceflight. The problem, as one can see, is that none of these engines can exceed the speed of light. Hence, Type 0, 1, and 2 civilizations probably can send probes or colonies only to within a few hundred light years of their home planet. Even with von Neumann probes, the best that a Type 2 civilization can achieve is to create a large sphere of billions of self-replicating probes, expanding just below the speed of light. To break the light barrier, one must utilize general relativity and the quantum theory. This requires energies which are available for very advanced Type 2 civilizations, or more likely, a Type 3 civilization.
So Kaku estimates that a Type 2 civilization would have matter-antimatter drives, like those on Star Trek, since those are what power Federation starships. But he envisions only the most advanced Type 2 civilizations and Type 3 civilizations actually being able to move faster than light.
Then let's talk about the latter. What should we know about Type 3 civilizations and their abilities?
Well, first, they are basically unkillable, at least by anything currently known to science. If you've spread out across an entire galaxy, then there aren't any disasters big enough and fast enough to wipe out your civilization. Even if your galaxy smashes into another galaxy, well, that's a slow motion disaster, and actually most of the stars will be just fine. In fact, our own galaxy, the Milky Way, has collided with and absorbed much smaller galaxies, multiple smaller galaxies. And it's scheduled to collide with the Andromeda Galaxy in about 4.5 billion years, leading the two galaxies to merge into a larger galaxy that has been dubbed Milkdromeda. That's not to say that there aren't hypothetical disasters that could kill a whole galaxy, like what's known as a false vacuum decay, also known as the Big Slurp. where the Higgs field that is responsible for objects having mass suddenly drop into a lower energy state and create a bubble of vacuum decay that expands outward, rewriting the laws of physics at the speed of light, and that could consume much or all of the universe. But we don't even know if such false vacuum decays are possible, and it would take some kind of disaster capable of quickly destroying large chunks of the universe to wipe out a Type 3 civilization. On the other hand, there are a lot of cool things that such civilizations could do, like the possibility of having faster-than-light travel. Kaku writes,
Special relativity states that no usable information can travel locally faster than light. One may go faster than light, therefore, if one uses the possibility of globally warping space and time, i.e. general relativity. In other words, in such a rocket, a passenger who is watching the motion of passing stars would say he is going slower than light. But once the rocket arrives at its destination and clocks are compared, it appears as if the rocket went faster than light, because it warps space and time globally. Either by taking a shortcut or by stretching and contracting space, there are at least two ways in which general relativity may yield faster-than-light travel. The first is via wormholes, which may give us a shortcut across space and time. One possible geometry for such a wormhole is to assemble stellar amounts of energy in a spinning ring, creating a Kerr black hole. Centrifugal force prevents the spinning ring from collapsing. Anyone passing through the ring would not be ripped apart, but would wind up in an entirely different part of the universe. This resembles the looking glass of Alice, with the rim of the looking glass being the black hole and the mirror being the wormhole. Another method might be to tease apart a wormhole from the quantum foam, which physicists believe makes up the fabric of space and time at the Planck length, 10 to the minus 33 centimeters.
However, while wormholes are theoretically possible, they may or may not be practical as ways of traveling faster than light.
The problems with wormholes are many. A. One version requires enormous amounts of positive energy, for example, a black hole. Positive energy wormholes have an event horizon and hence only give us a one-way trip. One would need two black holes, one for the original trip and one for the return trip, to make interstellar travel practical. Most likely, only a Type 3 civilization would be able to harness this power. B. Wormholes may be unstable, both classically and quantum mechanically. They may close up as soon as you try to enter them, or radiation effects may soar as you enter them, killing you. C. One version requires vast amounts of negative energy. Negative energy does exist in the form of the Casimir effect, but huge quantities of negative energy will be beyond our technology, perhaps for millennia. The advantage of negative energy wormholes is that they do not have event horizons and hence are more easily transversable. D. Another version requires large amounts of negative matter. Unfortunately, negative matter has never been seen in nature. It would fall up rather than down. Any negative matter on the Earth would have fallen up billions of years ago, making the Earth devoid of any negative matter.
Although that's not to say we couldn't find negative matter in space. However, there is another way of traveling faster than light that has been proposed. It's the principle behind what's known as the Alcubierre warp drive, which involves stretching space, because even though objects in space can't move faster than the speed of light, space itself can move faster than the speed of light. Kaku explains,
The second possibility is to use large amounts of energy to continuously stretch space and time, that is, contracting the space in front of you and expanding the space behind you. Since only empty space is contracting or expanding, one may exceed the speed of light in this fashion. Empty space can warp space faster than light. For example, the Big Bang expanded much faster than the speed of light. The problem with this approach, again, is that vast amounts of energy are required, making it feasible only for a Type 3 civilization. Energy scales for all these proposals are on the order of the Planck energy, 10 to the 19 billion electron volts, which is a quadrillion times larger than our most powerful atom smasher.
And if it is possible to travel faster than light, it also may be possible to travel through time, as we discussed way back in episode 29 at mysterious.fm/29. Kaku also discusses this.
Lastly, there is the fundamental physics problem of whether topology change is possible within general relativity, which would also make possible time machines or closed time-like curves. General relativity allows for closed time-like curves and wormholes, often called Einstein-Rosen bridges, but it unfortunately breaks down at the large energies found at the center of black holes or the instant of creation. For these extreme energy domains, quantum effects will dominate over classical gravitational effects, and one must go to a unified field theory of quantum gravity.
But we don't yet have a theory of quantum gravity. Kaku goes on to tout a version of string theory as a possible candidate here, and Kaku is a big advocate of string theory. But in recent years, string theory has fallen on hard times, and it's looking much less promising. Even Sheldon Cooper on the Big Bang Theory abandoned it. Nevertheless, Type 3 civilizations may well be able to build time machines. And even if they're not, there's still lots of really cool things and probably presently unimaginable things that Type 3 civilizations could do.
Okay, now next we'll move to the faith and reason perspectives. But before we do that, we want to take a moment to thank our patrons who make this show possible, including Josh C., Daniel H., Patricia J., Robert R., and Michael H. Their generous donations at sqpn.com/give make it possible for us to continue Jimmy Akin's Mysterious World and all the shows at StarQuest. And you can join them by visiting sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you by DeliverContacts.com, offering top brand contact lenses at always low prices with free delivery. Visit DeliverContacts.com. This StarQuest show is also brought to you by Exodus 90 and the Exodus 90 Challenge, which begins this year on January 20th. This isn't just a 90-day program. Exodus 90 is a spirituality for men in modern times built on 3 ancient pillars: prayer, self-sacrifice, and fraternity. We all long for something more, and that something is to be found in becoming the men that God created us to be, sons of a loving Father. It's time to turn away from our idols. It's time to break free from the pharaohs that hold us in bondage. If you're ready to make a fresh start, to break free, refocus, and rediscover who God is calling you to be in the new year, and embark on a journey to uncommon freedom in Jesus Christ, then download the Exodus 90 app today. We start January 20th, 2025, so go to exodus90.com/SQPN to learn more about Exodus 90. That's exodus90.com/SQPN. Join a once-in-a-lifetime opportunity to go on pilgrimage to the mysterious shrines and sites of Italy in the Jubilee year 2025 with Jimmy Akin and me, Dom Bettinelli. Go with us on a 12-day, all-inclusive tour that gives you incredible access to Jimmy's insights in Rome, Assisi, Orvieto, Monte Cassino, San Giovanni Rotondo, the Grotto of St. Michael, and more. We're also planning special activities like recording on location for future episodes of Mysterious World, and an in-person Weird Questions episode just for pilgrims. Space is limited and filling up, so be sure to find out more. Visit mysterious.fm/Italy 2025 to reserve your spot today. That's mysterious.fm/Italy 2025. So, Jimmy, what can we say about the Kardashev scale from the reason perspective? Anytime an idea is proposed in science, it's subject to criticism and cross-examination. Kardashev proposed this classification scheme back in 1964, over 60 years ago. So what kind of pushback has it gotten?
Well, we've already covered some of the modifications of it that have been proposed, like redefining Type 1 so it doesn't reflect power use in 1963, but a level that we may achieve in a century or two, and like Carl Sagan's refinement that allows levels between the major types, like having a 1.5 or a 2.6 civilization. And of course, the add-in of Type 0 as a civilization category, with us currently being at 0.73. Each of these reflects a form of minor criticism with a suggested fix. There also have been attempts to extend the scale upwards so that you get type 4, 5, or 6 civilizations. In his Civilizations article, Michio Kaku writes,
"How do we escape the death of the universe itself?" Astronomer John Barrow of the University of Sussex writes, "Suppose that we extend the classification upwards. Members of these hypothetical civilizations of type 4, 5, 6, and so on would be able to manipulate the structures in the universe on larger and larger scales, encompassing groups of galaxies, clusters, and superclusters of galaxies."
So this system relies on the fact that there are structures in the universe that are larger than galaxies. There are groups of galaxies which might host type 4 civilizations, larger clusters of galaxies which might host type 5 ones, and even larger superclusters which might host type 6. And with such civilizations, new possibilities might emerge. Kaku continues,
"Civilizations beyond Type 3 may have enough energy to escape our dying universe via holes in space." Lastly, physicist Alan Guth of MIT, one of the originators of the inflationary universe theory, has even computed the energy necessary to create a baby universe in the laboratory. The temperature is 1,000 trillion degrees, which is within the range of these hypothetical civilizations. Of course, until someone actually makes contact with an advanced civilization, all of this amounts to speculation tempered with the laws of physics. No more than a useful guide in our search for extraterrestrial intelligence.
and that's certainly true. This is just potentially useful informed speculation, not anything you should hang your hat on. However, there's a larger problem with the extension of the scale in this way, which is that there is no unanimity on what these higher types would represent. For example, the Hungarian futurist Zoltán Galantai envisions type 4 as using the power of an entire universe, and that leapfrogs the versions that Kaku just described. So there's no agreement on what the higher levels would correspond to, and authors conceptualize the higher levels differently.
That leads to your own major criticism of the Kardashev scale. Tell us about that.
Well, I note that in his 1964 paper, Kardashev only proposed the 3 types as a matter of convenience. And I think that if you treat them casually as just something of convenience, then that's fine. But what a lot of people have done is treat them as if they are hard and fast categories, and there are serious problems with that. For example, if you define type 1 as being able to use the power of a single planet, well, planets are different, and you can generate different amounts of power on different planets. For example, you can generate more power on Earth than you can on Mars or the Moon, whether you're doing that purely by solar power or by other means like hydrocarbons or nuclear fuel or wind or geothermal or whatever. Earth just seems to be a better place to make power than many other places. On the other hand, planets like Jupiter may have more power generating potential than Earth. So a planetary-based definition doesn't give you a single objective standard. The same is true of type 2s if you define them as using the energy equivalent to that of a star, because stars come in all different kinds and brightnesses, so they generate different amounts of power. And the same thing is true of galaxies. The galaxy we live in, the Milky Way, which the Type 3 category is based on, is an unusually large galaxy. Most galaxies are smaller, and some, like Andromeda, are bigger. The average galaxy is between 3,000 and 300,000 light years in diameter, so that's 2 whole orders of magnitude, or a factor of 100. So you'll get wildly different levels of power from different types of galaxies.
What's your solution to this problem?
Basically, to not worry about the types that we've been talking about as anything other than matters of convenience, like Kardashev said, and to instead focus on the actually objective scale that lies behind them. Carl Sagan helped put things on a more objective basis with his formula based on the number of watts that a civilization uses. That allows, classifications like 1.5 or 2.6. Under his system, a type 1.0 civilization would use something in the range of 10 to the 17 watts. A type 2 Point O would use something in the range of 10 to the 26th watts, and a type 3 would use something in the range of 10 to the 37 watts. But what's really important here is not the Kardashev type number, it's the watts that they use. So I'd say just ignore the type numbers as anything but matters of ad hoc convenience and focus on the number of watts. So presently, the Earth uses about 19 terawatts of power, which is in the range of 10 to the power of 13 watts. So under my system, I'd say we're a type 13 civilization. What corresponds to a Kardashev type 1 civilization would then be a type 17 civilization, since it uses something in the range of 10 to the 17 watts. What corresponds to a Kardashev type 2 would become a type 26. What corresponds to a type 3 would be a type 37, and you just keep going on from there. Every time you multiply your power consumption by an order of magnitude, or a factor of 10, you go up 1 point on the scale. That's a simple objective system that's easy to keep track of. It doesn't have an arbitrary system of additional numbers layered over it. It's not Earth-centric, Sol-centric, or Milky Way-centric. It doesn't depend on what kind of planet you're from, what kind of star you have, or what kind of galaxy you live in, or where the power you're using comes from. It allows for a much better and easier comparison of civilizations, because the difference between a Kardashev type 1 and a Kardashev type 2 is 9 orders of magnitude. And the difference between a Kardashev type 2 and a type 3 is 11 orders of magnitude, meaning that there are enormous differences between what a civilization at the low end of a Kardashev number can do compared to what a civilization at the high end of that same number can do. Another benefit of my system is that you don't have to use an additional formula to convert power usage from watts into something else. You just use the exponent of the number of watts they used, and that's just way simpler and easier. I've decided that if I ever write space opera where different civilizations are encountering each other, that's what I'm going to use to describe them. Just a straightforward classification of civilizations based on how many watts they use, allowing a much more direct comparison of the power of different civilizations and seeing how close or far apart they are from each other. So if I write a story where something like the Federation is meeting something like the Romulans, it might be an encounter between two type 30 civilizations. But if they go visit a primitive planet like ours, they'd be meeting a type 13 civilization. And all I have to do is use a single line of dialogue to explain this system, like, Captain, they consume 10 to the power of 13 watts of energy, so they're a type 13 civilization. Boom, done. Everything is clear.
Have there been other criticisms of the Kardashev scale besides the way it handles power consumption?
Yes, because mere power consumption isn't the only thing you'd want to look at or know about a civilization. So the Kardashev scale has been seen as being an incomplete way of looking at civilizations. For example, Carl Sagan proposed that it needed to be supplemented with a measure of how much information the civilization has. And he suggested using a letter of the alphabet for that, with type A civilizations having the lowest amount of information and type Z civilizations having the highest. A type A civilization, on his proposal, would have 10 to the power of 6 bits of information, or 1,000,000 bits of information is at its disposal. A type B would have 10 to the 7th bits of information. A type C would have 10 to the 8th bits of information, and so on. Sagan then combined this with a Kardashev number, and he estimated that in 1973, humanity would have been a Kardashev type 0.7H civilization, meaning that it used about 10 terawatts of energy and had about 10 to the 9th bits of information. While today, we would be a Kardashev type 0.73 R or S civilization, given the amazing leaps of knowledge that we've had in the last 50 years, even if most of it is trivia rather than big fundamental new discoveries. Sagan estimated that a galactic civilization would be a Kardashev type 3Q civilization, and that a federation of galaxies would be a Kardashev type 4Z.
What do you make of this proposal?
Well, I think that measuring how much information a civilization has is a good idea, though obviously there's a relationship between how much knowledge you have and your ability to make and consume power, so they're not completely independent from each other. Also, I'm not a particular fan of his using letters of the alphabet for knowledge because you're going to run out of letters. And the relationship is not as clear as with numbers. People may not remember where is, how far through the alphabet is S, and things like that. And there are also other things that you may want to measure about a civilization, like what its population is. For example, in Larry Niven's Known Space series, he has a race known as the Puppeteers. They're an advanced civilization, more advanced than humanity, but they're a herd species, and they're cowards who don't want to leave their planet. In order to leave their planet, they have to be literally insane. So they're not interested in building a multi-star civilization. Instead, they've got 1 trillion puppeteers living on one world. And they view Earth, by contrast, as a barren, unpopulated world with only a few billion humans living on it. So you also need to take into account what a civilization does with its knowledge and power. If it's like the puppeteers, it may be primarily interested in maintaining a large population and not doing much else. So the puppeteers might be a type 12 civilization in terms of population with 10 to the 12th or 1 trillion members, while humanity might only be a type 10 civilization in terms of population with 10 to the power of 10 or several tens of billions of humans scattered across known space. There have also been other proposals for scales of things to measure, like ranking civilizations by how small the things they can manipulate are, so that a civilization that can manipulate subatomic particles ranks higher than one that can only manipulate atoms. Another proposal is to rank them based on the types of disasters that they can withstand. And I think that in all these cases, people are proposing interesting ways of measuring civilizations, but they don't eliminate the utility of looking at power consumption the way Kardashev did. So I don't think they invalidate the Kardashev approach.
The Kardashev scale provides an interesting way to think about how civilization might develop and what kind of abilities they might have. But does it have any practical value to us today?
Potentially. You'll recall that the title of Kardashev's original 1964 paper was Transmission of Information by Extraterrestrial Civilizations, and that's what he was really interested in, and not the power consumption itself, but what civilizations might do with the power for purposes of communicating, and how we might detect such civilizations. So his efforts were focused on the search for extraterrestrial intelligence, or SETI. He made some initial proposals, and in later years, he and others made a bunch more. Since SETI isn't the topic of our show today, we won't go into these in detail, but I will mention a few things. First, listeners may know that we've been monitoring select radio frequencies for ET transmissions in select parts of the sky for a while, but we haven't heard anything that proves ET life is out there. Michio Kaku, among others, proposes that there may be a reason for this. In his Civilizations article, he writes,
"The current SETI project only scans a few frequencies of radio and TV emissions sent by a Type 0 civilization, but perhaps not an advanced civilization. Because of the enormous static found in deep space, broadcasting on a single frequency presents a serious source of error. Instead of putting all your eggs in one basket, a more efficient system is to break up the message and smear it out over all frequencies, and then reassemble the signal only at the other end. In this way, even if certain frequencies are disrupted by static, enough of the message will survive to accurately reassemble the message via error correction routines. However, any Type 0 civilization listening in on the message on one frequency band would only hear nonsense. In other words, our galaxy could be teeming with messages from various Type 2 and Type 3 civilizations, but our Type 0 radio telescopes would only hear gibberish."
So there may be a perfectly good reason we haven't heard any identifiable ET signals yet. On the other hand,
With their energy output comparable to that of a small star, more advanced civilizations should be visible from space. Dyson has proposed that a Type 2 civilization may even build a gigantic sphere around their star to more efficiently utilize its total energy output. Even if they try to conceal their existence, they must, by the second law of thermodynamics, emit waste heat. From outer space, their planet may glow like a Christmas tree ornament. Dyson has even proposed looking specifically for infrared emissions rather than radio and TV to identify these Type 2 civilizations.
And that's like the puppeteer world in Larry Niven's Known Space, with a trillion puppeteers all on the one planet and the technology that is used to support them. Their planet throws off a lot of waste heat, and it glows in infrared light. The same thing would be true even if a Type 2 civilization somehow built a Dyson sphere that completely surrounded its sun. We wouldn't see visible light coming off of the sun because it'd be blocked by the Dyson sphere. But in capturing and using all that energy, the conversion of energy to work wouldn't be perfectly efficient, and so it would generate waste heat, and that would cause the Dyson sphere itself to heat up and glow in infrared. So you could look for a solar system-sized patch of space that's dark in visible light but glowing in infrared, and that's one way you could find Dyson spheres. We could even look for this happening in other galaxies, and there actually are some possible candidate galaxies for this that have been discovered, where one half of the galaxy looks darker than the other half, possibly indicating a Type 2 civilization that's there, or rather, given the distance, that was there, and spreading throughout that part of the galaxy, building Dyson spheres or swarms and causing the stars in that part of the galaxy to look dimmer. It's also possible that some of the very bright radio objects that we see in other galaxies might be technologies built by Type 3 civilizations, and there have been some candidates here as well.
Haven't most or all of those been classified as natural phenomena like quasars?
Yeah, but here's the thing. Some of them might be artificial, but we're not recognizing them for what they are. Let me give you an analogy. Suppose that you're a dog that lives in a big city, and as you wander around your neighborhood, you see trees, which are naturally growing organisms, but you also see fire hydrants, which are technological artifacts. Being a dog, you don't know much about trees or fire hydrants. I mean, you're primarily focused on the urine-based internet communication system that dogs use trees and fire hydrants for. But you've never seen trees visibly grow in or fire hydrants being installed by workmen. So you just tend to think of both trees and fire hydrants as things that exist in your environment, apparently naturally. With your limited dog-based knowledge, that'd be a logical conclusion, as what you know about your environment is based on your own observations. Since you can't understand human language, no one can tell you any different. Well, the same thing's true of us. Everything we know about the universe is based on our own observations. And so some of the radio sources that we see might be like trees, just natural phenomena that grow and develop on their own, while other radio sources that we see might be like fire hydrants, technological radio sources that we assume are natural, but aren't. There's actually a debate about this among some SETI researchers, and there are some possible candidates for artificial radio sources. It's just that they're controversial, and we need to know more. But it's possible that we've already detected advanced civilizations, particularly outside of our galaxy, and just not recognized what we're looking at. We need to know more to figure that out, and we may well find out more since our studies of the sky are far from complete and there's lots left out there to be discovered.
Let's close by looking at the Kardashev scale from the faith perspective. What can we say here?
Well, from the faith perspective, there's no reason that extraterrestrial life can't exist. If God made intelligent life capable of technology here on Earth, then he could make it elsewhere in the universe. So there's no threat to the faith from that idea. There's also no reason why God couldn't allow it to grow to type 1, type 2, or type 3 status, or even beyond. God can do what he chooses to do and allow what he chooses to allow. In this case, in the case of humanity, I think it's unlikely that he'll let us get beyond type 1. It's fun to imagine what it would be like if we had a Star Trek-like civilization and faster-than-light travel, and spanned hundreds of star systems. That makes for interesting science fiction. But based on what the Bible says about the end of the world, I suspect that we're going to be confined to our own solar system when Jesus comes back, though we may have sent a few probes to other stars.
The question is then whether God would do the same for other civilizations in the universe. If they exist, do you think God would do the same thing for them?
I don't know. If we take our example as representative, if I'm even right about our example, if we take it as representative of what God does in general, then, well, yeah, I think he would do the same for them. And so there wouldn't be any type 2 or type 3 civilizations out there. But we have to be careful judging things by our own example. I mean, we only have a sample size of 1, and n equals 1 is not a firm basis for making an inductive argument. We have a really good illustration of that with the structure of our own solar system. Before we started discovering planets in other star systems, all we had to look at was our own. And it was assumed that other star systems with planets would look a lot like ours, with small terrestrial planets near the star and gas giants like Jupiter and Saturn farther out. But then, when we actually started finding exoplanets, this turned out to be wrong. Among the first things we discovered were so-called hot Jupiters, or gas giants that were very close to their suns, like at the distance of Mercury or something. So it turned out that our solar system looks more like an outlier. And if that's true of the structure of our solar system, it could also be true of how God deals with the races that could inhabit other star systems. Maybe our race is an outlier. Maybe God will bring our race to its consummation before we get past type 1, but maybe he lets other races get past that mark. In fact, if the idea that God is glorified by the diversity of things he creates is true, then you could even expect that he would do this for different races and further glorify himself by having different paths that races can follow. Or they might fall into classes. Maybe if a race falls into sin like ours and has to be redeemed, well, then God brings it to consummation before it can get out of its solar system and start causing damage elsewhere in its fallen state. But if a race never falls into sin, he lets it spread out and achieve type 2 or type 3 status, since it will be positive and constructive rather than negative and destructive to other races. Or maybe unfallen races, or some of them, just stay on their own planets in paradises like the Garden of Eden. Or maybe it's a mix of all of these outcomes that all glorify God. At this point, there's no way to know, so we have to leave this matter in God's hands.
So, Jimmy, what's your bottom line on this topic?
The Kardashev scale is an interesting way of classifying how civilizations may be developed. It's useful as a tool of convenience, but I prefer raw power measurements as a simpler and more objective scale. There are also a bunch of things besides power consumption that need to be measured about a civilization, but the Kardashev scale is a useful tool for thinking about advanced civilizations and what they may be able to do. And it may even help us find some of them in the search for extraterrestrial intelligence.
And what further resources can we offer to the listeners and viewers on the topic?
We'll have links to Michio Kaku's book, The Physics of the Impossible, John Horgan's book, The End of Science, a link to an English version of the original 1964 paper by Kardashev, also Kaku's article, The Physics of Extraterrestrial Civilizations, and his article, The Physics of Interstellar Travel. We'll also have links to the Great Filter Hypothesis, the Silurian Hypothesis, and John Horgan's new doubts or later doubts about his book, The End of Science, and a video by Zabina Hassenfelder reviewing his book and the End of Science debate. We'll have a link to Philip Metzger's paper, Nature's Way of Making Audacious Space Projects Viable, Nicholas Loris on Drilling Our Way Out of the Problem, the average U.S. price of gas not adjusted for inflation, and a U.S. inflation calculator so you can do all of the adjusting for inflation to your heart's content that you want based on the inflation the government causes.
And now it's time to hear from you. What are your theories about the Kardashev scale and its implications for extraterrestrial civilizations? Let us know by visiting sqpn.com or the Jimmy Akin's Mysterious World Facebook page. Send us an email to feedback@mysterious.fm. sending a tweet to @MYS_world, visiting the StarQuest Discord community at sqpn.com/discord, or by calling our mysterious feedback line at 619-738-4515. That's 619-738-4515. I also want to thank Rob Mady for his voiceover work on this episode.
And I want to say a special word of thanks to Oasis Studio 7 for the video and animation work in this episode. You can hire them and to do your own video and animation work, and you can check out what they do by going to my YouTube channel, youtube.com/Jimmy Akin. While you're there, at the time of recording, I'm really trying to reach 100,000 subscribers because that's a major milestone for YouTubers, and I suspect that once we hit that, the YouTube algorithm will be more generous and I'll be able to reach more people. So you can help me do that by liking, commenting, subscribing, and be sure and hit the bell notification when you subscribe so you always get notified when there's a new video.
Jimmy, we could refer to it as the YouTube Type 1 channel for 100,000 subscribers.
Trying to get to Type 1, yes.
So what's our next episode going to be about?
Next week is a Fifth Friday, so we're going to be doing our usual Fifth Friday weird questions, and we're going to be looking at topics like whether AI is a demonic illusion, what we know about Jewish Nazarene Christians, what type of angel the devil was, who Alfred E. Neumann was, what begotten not made means, whether time travel violates natural law, whether God can change his mind, and a whole bunch more.
Excellent. Folks, be sure to check out the Mysterious World bookstore at mysteriousworldstore.com for links to all the books and videos that Jimmy mentions in the show. Get your very own Mysterious World t-shirt, mug, and more in our merchandise shop at sqpn.com/merch. You'll find links to Jimmy's resources from our discussion on our show notes at mysterious.fm/348. And remember, to help us continue to produce the podcast, please visit sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you in part by Rosary Army, featuring award-winning Catholic podcasts, rosary resources, videos, and the School of Mary online community, prayer, and learning platform. Learn how to make them, pray them, and give them away while growing in your faith at rosaryarmy.com and schoolofmary.com. And by The Grady Group, a Catholic company bringing financial clarity to their clients across the United States, using safe money options to produce reasonable rates of return for their clients. Learn more at gradygroupinc.com. Jimmy Akin's Mysterious World is also brought to you in part through the generous support of Aaron Vergeson Electric and Automation, making connections for life for your automation and smart home needs in North and Central Florida at aaronv.com. Until next time, Jimmy Akin, thank you for exploring with us our mysterious world.
Thanks, Tom.
And once again, I'm Dom Bettinelli. Thank you for listening to Jimmy Akin's Mysterious World on StarQuest.